Hey, Dr. O here, and today I'd like to talk about ventilation-perfusion coupling. When we're talking about ventilation-perfusion coupling, what we're talking about is ensuring that the rate of air that's moving in and out of the air sac in the lung is matched adequately with the amount of blood that is flowing by in the pulmonary capillary bed. And when that is adequately matched, what we're going to see is that carbon dioxide is going to come out of the blood and oxygen is going to upload into the blood at a rate that's about equal and capable of sustaining life. Now, as you can imagine, there's a great deal of detail that we could look at when it comes to ventilation-perfusion coupling, such as taking a look at the rate of ventilation given the quantity of blood that's flowing by, and look at how it varies over the area of the lungs, because what happens in the apex is certainly different from what's happening at the base. But that's not this video. In this video, I want to explain the concepts that are driving ventilation-perfusion coupling so that you can later come back and understand all of those subtleties of it. So let's get started. When we're talking about ventilation-perfusion coupling, certainly we're talking about the alveolus in the lung as well as the pulmonary capillary. And we have to take into consideration the partial pressures of the gases that we're concerned with in each of these systems to understand what's driving the behaviors of these gases. In the capillary, the partial pressure of oxygen comes in at 40 millimeters of mercury, and the partial pressure of carbon dioxide comes in at 45 millimeters of mercury. In the alveolus, the partial pressure of oxygen comes in at 104 millimeters of mercury, and the partial pressure of carbon dioxide comes in at 40. So when we start comparing these numbers, we can see that oxygen in the alveolus under 104 millimeters of mercury wants to move from the alveolus into the capillary, where it's only 40 millimeters of mercury. And for carbon dioxide, we can understand why it wants to move from the capillary, where its partial pressure is 45 millimeters of mercury, to the alveolus, where the partial pressure is only 40. So when we look at these two systems, the systems of pressure in the alveolus and the systems of pressure in the capillary, we can understand what's driving diffusion. It's the concentration gradients established by the differences in the partial pressures of each of those two gases. But ventilation doesn't start and stop in the alveolus. There's one more system we need to take into consideration, the atmosphere, because we're doing a gas exchange with the atmosphere too. Now, in the atmosphere, the partial pressure of oxygen is going to come in at 159 millimeters of mercury, and the partial pressure of carbon dioxide comes in at 0.3 millimeters of mercury. Now, looking at this system, we can certainly understand why oxygen will be driven into the lungs, and we can also understand why carbon dioxide would be driven out of the lungs. So as we look at what's happening between these three systems, we can start to see, starting in the capillary, we can see that carbon dioxide is going to be encouraged to move from that environment where the partial pressure is 45 millimeters of mercury to the alveolus where the partial pressure is only 40. And then it will be further encouraged to move to an atmosphere where its final partial pressure is 0.3 millimeters of mercury. And the reverse is going to be true for oxygen. We can now see why oxygen is going to be encouraged to leave the atmosphere, where its partial pressure is 159 millimeters of mercury, and to be taken into the alveolus, where the partial pressure drops down to 104. And then be further encouraged still to enter into the bloodstream, where the partial pressure is 40 millimeters of mercury. But what happens when something goes wrong? Well, let's have a look at that. Let's say that we have a sick alveolus, an alveolus that can no longer bring in air. When the alveolus can no longer perform ventilation, then the system that provides that air is going to be removed from consideration. That means the atmosphere. So without the bringing in of air from the atmosphere, we don't have to take into consideration the effect of those partial pressures. And this means that the only two systems that we need to be considerate of are the pressures that are involved with the alveolus and the capillary. So what's going to happen? Well, the oxygen that is currently in the alveolus will continue to offload and go into the bloodstream. But as more oxygen leaves the alveolus and enters the bloodstream, the partial pressure of oxygen in the alveolus begins to decline. In fact, it will decline to the point where it becomes equal to that of the partial pressure of oxygen in the capillary. And what about carbon dioxide? Well, carbon dioxide will continue to offload until the partial pressure of carbon dioxide in the alveolus equalizes to the partial pressure of carbon dioxide in the capillary. And what this means is that the next little bit of blood that shows up, there'll be no place for the carbon dioxide to go, and there'll be no more oxygen available to offload into the blood. So there won't be any sort of gas exchange that takes place. So without the influence of this third system, the system of the atmosphere, these two systems will basically equalize to each other. Now, the lung is going to be well aware that the partial pressure of oxygen in the alveolus went from 104 millimeters of mercury all the way down to 40. And in response to this, the lung understands that no oxygen exchange is taking place, no carbon dioxide exchange is taking place. And as a result, it's going to trigger the arteriole feeding that capillary bed to shut down and send that blood to a functioning alveolus. So to summarize all this, we can say that low alveolar partial pressure of oxygen causes arterial constriction. But what if it isn't the alveolus that's sick, but the capillary? Well, let's have a look at that. Now, in this scenario, we have lost blood flow through the capillary bed. So what's going to happen? Well, gas exchange will occur, but only to the point where it exhausts what's in the alveolus. And then because there's no more blood flow, there's no carbon dioxide to offload, and there's also no call for oxygen. So essentially, the system of pressures formed from the capillary get eliminated, leaving the only two systems for us to consider being the systems of pressure in the alveolus and the systems of pressure in the atmosphere. Now, just because blood flow has stopped doesn't mean that ventilation has stopped. In fact, ventilation continues with air coming in and then air going out. And with every breath in and out, the partial pressure of oxygen in the alveolus starts to resemble that of the partial pressure of oxygen in the atmosphere. And likewise, the partial pressure of carbon dioxide in the alveolus comes to resemble that of the partial pressure of carbon dioxide in the atmosphere. Now, the lung becomes well aware that the partial pressure of carbon dioxide in the alveolus is dropped from 40 millimeters of mercury all the way down to about 0.3. And that this means that there's no gas exchange happening with the capillary. And if there's no gas exchange, then there's really no reason to send air into this alveolus. So the lung responds by shutting down the bronchiole. So to summarize this scenario, we can say that low alveolar partial pressure of carbon dioxide causes bronchial constriction. In the past few slides, we saw that if we had a decrease in the partial pressure of oxygen in the alveolus, that this would cause the arteriole that was feeding that capillary bed to constrict. And we also saw that if we had a drop in the partial pressure of alveolar carbon dioxide, that would cause the bronchiole to constrict. But what if either one of these partial pressures was to increase? Well, let's say that we had the alveolar partial pressure of oxygen go from 104 millimeters of mercury up a bit to 106. In this case, the higher alveolar pressure of oxygen would cause the arterioles to dilate. Now, why is that? From the body's perspective, the lungs would be saying, look at all this oxygen I have available. I should get some more blood over here to this alveolus. And the way the lungs make that happen is to trigger the arterioles to dilate. And what if we had a slight increase in the partial pressure of carbon dioxide in the alveolus? Well, from the body's perspective, the lung would say, wow, I must be having a lot of blood show up at that pulmonary capillary, and it's dropping off all this carbon dioxide to the alveolus, so I better expand the bronchiole to ensure that the carbon dioxide leaves and get more oxygen coming in. And then the bronchiole would dilate. Now, this is probably the best slide in the entire presentation because it gives you kind of a cheat sheet about what happens when partial pressures in the alveolus change. And in fact, it is the partial pressure of the alveolus changing that drives the constriction or dilation that we see either in the bronchioles or the arterioles. And with that, my friends, we are done. Thanks for watching.